Okay, hi everybody. Today we are going to be looking at Glasgow again, and we're going to be playing with the auto baud feature, so or baud, however you want to pronounce that. So the idea with Glasgow here is that we can have a UART implemented in the gateway, and we can connect it to another UART. So I've just got an FTDI adapter here, and we should be able to communicate with the Glasgow at any baud rate we like, and it should be able to then pick up the baud rate and mirror it, basically. So what we're going to do is wire this up in such a way that I can actually probe the lines and get some good confidence in what's going in. Not sure, we can't necessarily guarantee that, for example, the FTDI chip here is giving the precise baud rate we expect. There's always some tolerance with this sort of stuff. And so what we're going to do is actually have a scope on there so we can be confident that the baud rate we are configuring is actually coming out. And then once we've got that sort of level of assurance, we can start to work with the applet and figure out what's going on. So as always, we need a ground connection. I'm just going to use these long flying wires so that we can get a ground connection. I'm going to hook that up with the crocodile. Slow signals here, so we don't really worry too much about the the length of these cables. I'm just going to confirm the Glasgow's UART applet. It has some options, so you can configure which pin is the transmit and which pin is the receive. And I want to hook into the receive pin, so that's the transmit pin of the FTDI. I'm going to then hook in and just capture it on the scope. So by default, I had this configured last night when Esben found the problem. So this is all left over from yesterday. So I'm going to connect up pin 0 here, which is the receive pin, is going to be this orange one. So we're just going to sort of intercept that signal. Grab that out there. Oh, come on. There you go. And I'm going to feed one of these green wires in its place. That's then going to come over to this breadboard. And I'm going to put one of them immediately back and into the orange we've just disconnected. So that's connected up as exactly as it was yesterday. And then the other one I'm going to connect up to the scope. Like that. There we go. So hopefully that all makes sense. I was thinking as well we could probably connect up an LED just to see it blink. So the UART will idle high, which means that we want to connect the 3.3 volts to the pin, and then we can get a little blink out of it. So if we just put a little resistor in there, I've just got a red LED out of the box. Put a resistor in, that's about 330 ohms, I think it was. And then the negative end of the LED to the resistor. And I'm just going to go and grab another wire. And then we can do the positive supply voltage from the Glasgow to the positive end of that LED. And then we should get a nice blink every time we see a transmission. So that just gives, again, more confidence that this is actually behaving the way we want it to, the way we expect it to. So hopefully you can all see that LED nice and clearly. Then we need to plug everything in. So I've just got a USB extension cable here, which is going to connect up to the FTDI port, like that. And then I've also got a micro USB cable. Again, that's got my little USB reset button. Oops. USB reset button so that I can reset the Glasgow. It's also got the test points and things. Quite a handy little board. And that's going to go there. Glasgow springs alive. Brilliant. Okay, right now if we just go back to the computer, and step one is to just find out where that UART came up. I've possibly got some others connected to this system, so we're just going to have a look at tail minus N50 of D message. We can see there's a big jump in time here, so that's probably yesterday, and then this will be today. And we can see there's TTY USB 1, and then there's the Glasgow. So I'm just going to keep hold of that, because that's the serial number, so we'll need that. I've got 2 Glasgows connected to this computer. And then here's TTY USB 1. So if we go for picocom -B115200 dev TTY USB 1, we should be able to make a transmission. I can see that on the scope, but the LED isn't lighting up. That's a bit unexpected. Turn it round just in case. There we go. Oh no. Never mind. Maybe let's ignore the LED. Okay. In that case, I'm just going to go and tweak the scope quickly. Okay, we should be able to see that. So if I send some characters, there they are. They are not looking very happy though. So first things first, we've got a voltage there of about 2.5, which is not correct. It should be more like 3. This could be because the Glasgow's playing around with it. So let's just disconnect that, try again. There we go, much better. I think maybe the Glasgow in its default reset state isn't as high impedance as we might expect on those pins. Oh no. Very interesting. Not sure what was going on there. Just for good measure, I think I'll turn on the serial decode. Actually, no, I won't, because we're going to change the baud rate so often. It's probably not worth having that. Anyway, that's the UART. So I can send an A, and then a B, C, D, etc. The period. So what we're really looking at here is the baud rate is the most narrow, the bit time, so the most narrow of these pulses here. We've got a positive width of 8.63 microseconds. So if we send an A, for example, we get the start bit, and then we get the 8th, or the most significant bit of the word. So that gives us this 8.66 microseconds. And then if we take an 8.66 millimicrosecond, so if we do 1 over that, sorry, we get 115,200-ish. So it's not actually 115,200, but it's sort of nearly there. Maybe the LED, it might have been, yeah. I'm a bit surprised by that, to be honest. So if we've got, oops, dropping the LED in there. We've got, yes, the output there. Oh, of course, because the LED is connected to the Glasgow, and the Glasgow's power supply is not currently on. It's not taking the supply from the FDDI chip. If I put you back on the scope and I put some more characters in, oh no, it still looks okay. Anyway, never mind. Okay, so that's the serial port. The scope is all set up. Let's do Control AQ. We can get out of picocom. I'm just going to take my jumper off real quickly. Okay, so if we set up Glasgow, we're going to need to give it a serial number. Grab that from off screen. Run UART, and then put TTY in there. What else do we need? Oh, the voltage, so we can say run UART minus capital V 3.3. There we go. That's now building, and I can put picocom on here. Okay, and if I now, there we go. If I now type a character into picocom, coming out of the FDDI port, the LED will just blink. You can just about see that on stream, I think. So it's good for me. You might not get lots out of it, I'm afraid, but again, it's just a confidence thing. Okay. So what we see straight away on the computer is all of these problems. What we want to do is set the auto board and just have a play with it quickly to kind of get a feel for what's working, what's not working. So if I just type some characters, there we go. It's picked up 9623 baud and it's getting the characters correctly. So if I type hello, there we go, 123, 123, and the carriage return new line's not being twisted around, but I think that's okay. We can just ignore that and put some spaces in. If I show you the scope, then we can have a look at this signal. I'll do an A again. That's our familiar territory. And again here we see there's 103.9 microseconds, and we can then put that into the calculator. 1 over 103.9 microseconds is 9624. So it's not really 9600, it's a little bit off. And actually Glasgow's doing pretty well there, 9623. It is a little bit off, but that's kind of to be expected. And UARTs can typically tolerate around about plus or minus 5% on the baud rate. So it clearly picks up 9600 baud, no problem. The scope's happy as well. I might just add the scope to this view again so that you can see that too. Grab that. There you go. I'll just pop that there. So yeah, we can see the characters coming through. It's picking up 9600. So now what happens if we turn the baud rate up? So Control B, Control U, Control A, Control U will turn the baud rate up to 19200 baud. And again, if we just type into here, we should get some problems potentially in Glasgow, but we don't see anything. And this is what Esden was seeing yesterday, I think. Looking at the scope, we can see now that we've got a width of 104. Let's do an A, sorry, there we go. 52 microseconds pretty much. And then again, 1 over 52 microseconds is 19200 pretty much. And that's within tolerance. So the baud rate has changed, but Glasgow is missing it for some reason. Now we need to dig in and try and see why. So if I quit Glasgow, start it again, I think the other thing that we noticed was that if you start at 115200, I say hello, it comes straight down, that's the default baud rate. If I then reduce it down to 57600, it picks up the problems and then it changes the baud rate, so that's okay. I reduce it down again, garbage, garbage, garbage. Ooh. Okay, not super happy with that. The scope looks like it's changed okay though. I'll change the baud rate down again. Garbage, garbage, garbage. There we go. Oh, actually, interesting there. It saw the previous baud rate and then it continued and actually switched over again. So something maybe edge related, counting the edges going on there. So that's 19200. If I then drop it down again, garbage, 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 and then it locks on. And then coming up again, we just see nothing. We can go up as high as we like. Now, I think I found some of the potential problems yesterday, but I'd like to walk it through with everybody. Zoom in a bit there. Hopefully it'll be somewhat useful. That doesn't fit on screen anymore. There you go. Hopefully a bit useful. So, right, let's just start hacking away at the Glasgow applet itself. We are going to have a look at the interface, I think it is, UART init. This is the correct one. Okay, cool. So the thing I think we're mostly interested in is this auto baud module here. And what it does is it looks for the shortest width, as in between two edges, it will try and find the shortest over a number of edges. So here it's configured by default for 32 edges. And then this state machine, this is effectively the reset state. If it's counted up to the 32, it will then produce the value that it's found, and it will start itself again. Otherwise, it will keep counting up to the 32. And then it resets the cycle counter. So everything is clocked here. And basically, we're counting the number of clock pulses between edges. We then advance into the count state. Each time around, we increment that counter. And we say here that if we've reached the latch value, which is initialized by default to all ones, so that's the overflow condition pretty much. If we reach the latch value, then skip the rest, because we've already found an edge short, or a pulse shorter than this, basically. Otherwise, if we found an edge, then we keep the current counter value and we start again. Hope that kind of makes sense. So the idea being here that let me just put you down on the table. What we're looking at really is UARTs produce these start bit, and then you've got a number of 8 data bits, so there's going to be 8 of them. All right, 1, 2, 3, 4, 5, 6, 7, 8. And then you have a parity bit, and then you have a stop bit, which is high, sorry, ignore that line, and then it carries on. All right, so depending on the value you're transmitting, say we've got an A, if I have a look at the ASCII table, and a little a is 61 in hex. Okay, so 61 is going to be 1, 0, 0, 0, and then 6 will be 0, 1, 1, 0. I think that's right. So what we actually have, the waveform then will be low for the start bit, low for the first, and then it'll be up, up, or high, high, sorry, low, 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 high. The parity, we've actually configured it to not have parity, and then you have the stop bit there. Start, stop. And this is optional. So what we see here, that's interesting because that doesn't seem to match up with what we were seeing on the scope just now for a little a. A quick look at that again. If I put you on the scope, we do a little a. There you go. Oh, am I doing MSB, LSB backwards? Yes, I am. Okay, apologies, everybody. So actually, okay, UARTs shift out least significant bit first. I'd clearly forgotten about that one. Let me just confirm that. MSB is transmitted last, yeah, okay. Cool. In that case, this waveform is incorrect. Apologies, everybody. What we actually end up with is a start bit, followed by the 1. So that's what we saw previously. And then we got 1, 2, 3 bit times of 0. And then we've got a 0, 1, 1, 0, and then the stop bit. Start, stop, no parity at the moment. So what we're measuring then, if we were to run our algorithm over this trace here, is we'd count up and up and up and up. We'd get to this edge, we'd start again, we'd count up and up and up, get to this edge, and we count up and up and up, but we've not found an edge, so we just skip it all the way to here, and then we reset, count up and up and up, and we haven't found an edge, so we skip it. Okay, so if you look at the counter, you have that basically. Where here is the skipped section. And when we skip, we stop the counter because there's no point looking at that anymore. We just wait for the next edge. And the fact that we've got the short edge right at the beginning means that we set the hard limit on here. Okay, so if we come back, have a look at the code again. What we have then is this, sorry, let me just gather my thoughts. Yeah, so what this will do is it will find the shortest bit time in the bit stream. And I'm not sure if this is working correctly, so I think it probably is, but let's get the values out of this into the computer so we can see them. So first thing to do, or the easiest way to do this, I think, is to put them into registers, basically. Let me just turn off the scope quickly. There we go. Actually got two scopes. Need to remove one of them. There we go. Okay. So we want to put these into registers. We've got the sequence count, the cycle count, and the cycle latch. And just having some visibility into that is going to help us out when we try and debug this. There are probably better ways to do this, but I'm just going to go with the way I know. So we're going to make some more registers here in the build step of the applet. And so we've got the seek count. (32 bits, might as well. And then we've got the cycle count and the cycle latch. And then we need to pass them into the applet. So we're going to put them in here. I'm just going to make a tuple. I'm going to call it AB just because I'm lazy. And then we're going to take each of these registers into that tuple, which we can expand out inside the applet. Okay, so we come into the main UART sub-target, which is what we're passing into on the right-hand side there. We get AB here, self.ab equals AB, and then auto board, we give it the AB, self.ab as well. So those registers are now available in the auto board module. We can then collect them here, so AB just there, and self.ab equals AB. And then we can just simply replace these signals with those registers. Self.ab 0, and we can do, it's 1 and 2, just because it's a tuple, like that. And that should rebuild okay. Let's give that a go. Should be basically no change from before. It's just that it's storing them in registers now instead of in in a register, but it's now accessible to the computer. Okay, so that's running. If we put some characters in, I see the LED blinking. There we go, we've latched on to 9600 and we see the A's out. A, B, C, D, E, F, etc. That's okay, but we can't see what those values are. So let us look at that in the application. So if we scroll down in the applet, there's the build phase, the run phase, and then finally there's the interact phase. And the interact phase is the bit where we end up when we can type into Glasgow and it should send it out of the serial port. We're using let's use the monitor errors task here. And I think we should be able to, so here's the baud rate switch notification that we see. So if we have a look back, we can see here it says 36 frame or parity errors detected, and then it says switch to 9600 baud. So in this task, it's just a forever loop. We can add in the other registers. So let's grab sequence count. Width is 4. And then we also want to grab the cycle count and the cycle latch. And the cycle latch. Okay, so now we've got them, we can print them out. So I'm just going to be really lazy. I'm not going to use the log or anything. Honestly, I'm not terribly familiar with it, and I quite like these printf syntax, or f-string, sorry, syntax that you get here. So new bit cycles, and we've got seek count, cycle count, and cycle latch. Okay, so if we now run the application, or the applet, sorry, there we go, we're getting these values out. 415, if we just put that through the calculator quickly, we have a 48 megahertz clock on Glasgow at the moment, so 48 megahertz kilomega divided by 415 gives us 115,200-ish, pretty much. That's sort of within tolerance. And so that's what it defaults to. Now, if we start sending it characters at 9600, what we should see now is that if I send it one character, I'll turn the scope back on so we can all see. If I send it one character, there we go. What we see there is we've got 7 edges counted, and we've counted as the cycle counter is about 5,000. So if we have a look on the scope, we've got 1 edge, 2 edge, 3 edge, 4, 5, 6. 1, 2, 3, 4, 5, 6. I think it starts at 1, is that right? Instead of 0. So yeah, so sequence count starts at 1, so that's okay. So that all adds up. Now the shortest after a single frame is apparently 5,000 ticks. So if we grab a calculator again, we do 48 megahertz divided by 5,000. Oh, look at that, 9600. So that looks like it's latched on fine, no problems. And if we give it a few more, we'll see the sequence counter rise, and then when it finally crosses that 32 edge threshold, oh, there you go, we've switched to the new baud rate. Now if I raise the baud rate to 19200, just see what happens. We give it a couple of edges, you can see on the scope that the frame size has shrunk. And now we see 2,498, 97 clock pulses per bit time, or per smallest pulse. And if I give it a few more, what happens? Okay, so nothing happens. Well, I mean, it kind of does. The cycle latch is now looking good. Let's have a quick look in the calculator again. We've got 48 megahertz divided by 2497. What do you reckon that is? 19200, pretty much. That's bang on what we're expecting. But the issue now is that the bit cycle, the new bit cycle here, is still stuck at 9600. Now, what I came across last night when I was playing with this is that if we have a look at the code, go to the scope again for a sec. The way this works is that in the UART subtarget itself, if we've turned on auto baud, then if we have a received frame error or a parity error, and the auto baud rate that we've detected is not just FFFF or all ones, then we assign the new value. But the problem is, if I come back to my trusty pad, with UARTs, say this one here is at 9600. If I then draw the same frame again, but at 19200, for example, the difference is going to be this. So each bit is going to be shorter, so that's 2, 3, 4, and we get two ones, a 0, and then it goes up to 1. There you go. Now, who can spot the problem? UART is framed by a start and a stop bit, but this stop bit here looks identical to what it should see at the end of a 9600 bit or 9600 baud frame. The issue is that there's no frame error and there's no parity error if we're just doing individual characters. So I think what I'm going to do, come back to the computer, why don't we try sending a bunch of characters all at once and see what happens instead of individual characters. So I've used Picocom here to configure the UART. I can now quit and I can just do echo hello directly into dev tty USB1. And we have a look at the scope. I think I might have got a dodgy wire in there, so get that back happy again. Oh, there we go, that's what the problem is. Okay. I'll turn the scope on again. And I'll send my hello. Oops. There we go. And I'll send my hello. And what we actually should end up with is a number of characters back to back. Quite sure why it's not come through like that. There we go. And if we were to decode that, we would see that this would be the character's hello. I'm not going to do that on the scope, but just take my word for it. I think that there might be potentially a couple of other frames off the end of the trace here, so it might be just the first few characters, or the last few. And it's fairly stable, so it might be the whole thing. So let us reconfigure for 9600. Give some A's, and you can see here that Glasgow is switched to 9600. And now let's configure for 19200 again. Give some A's, and we can see that our cycle latch here is changed, but the bit cycle value here is still stuck at about 5000. So if I quit picocom and I send hello all at once, a couple of times potentially, oh, there you go, immediately. So it's now latched on to the 19200. So that's kind of okay if you're communicating with a terminal or something that's spewing out a lot of data. But the edge case, I guess, is that individual characters don't come across very well, or they don't allow the auto board to work because of this issue with the framing. The fact that we have an idle line which looks identical to a stop bit, there's no frame error. The fact that we haven't got parity means that we can't have a parity error. We then end up with this situation where the new baud rate that we've just detected is never going to get applied. So I think because of what we can do with Glasgow, we can, let's just get out of that. What have I done? There we go. Because of what we can do with Glasgow, we can actually change the gateware on build. The auto board here is actually a register, I believe, which is why it's done at runtime. But the parity is configured at, I think, build time. Let's just have a look on the right-hand side here. Just get rid of the scope again. Here's the build. And the build arguments, parity is a build argument. So if you were to change the parity to 0, 1, odd or even, and run again, it would have to rebuild the entire applet. Hi, Maegus. Good to see you. We're playing with the Glasgow UART applet. Not sure if you saw... oh, no problem. Glad you received it. Not sure if you saw Eston's stream last night, but he found there were problems with the auto board detection. So if you were to change the parity and then rerun Glasgow, it would have to rebuild the applet, which means that we can actually use this argument here to determine whether or not potentially we should be looking for a parity error. So when you send an individual character and raise the baud rate from the previous value, you will never see a framing error. And if you don't have parity, you will never see a parity error either. So what we can do in here potentially is just tweak this to say, what does parity look like? I think it's probably just the string passed in. Yeah, args.parity, and that's going to be none, 0, 1, odd, even. So we can say if parity equals none, then perhaps we just always want to use the newest value. Else, if we have parity, at this point we can start looking for a parity error. The framing error only becomes relevant, as I said earlier, when you have multiple frames very close together. So this frame error, could we include that, or do we, because we've discard the fact that we're looking at parity. Oh, actually, hang on. We need to keep the test for all ones. There we go. But I don't think we need either of the others. There's no point looking at parity because we haven't got parity. And there's no point looking at framing because individual characters won't trip it up. That actually kind of means that there's almost no point looking at framing here either. So we're only going to look at parity and checking that is not all ones. So let's see what happens now if I rerun the applet. Oh dear, parity is not defined, okay. Let's go self.parity. Has no object parity. Oh, okay, it's passed directly into this UART module here. So that is in gateware UART. And in here, I think it probably gets stored on itself, yeah. So we can just say if self.uart.parity is none, then just update it all the time. Okay, see if that works. Looks promising. Okay, so we're configured by default again for 115-200. If I send a couple of A's, let's get the scope back. Oops, sorry, clicking on all sorts of things. If I send a couple of A's, there we go, frame or parity errors detected. There we go, there's the A, and we've latched onto the 9600 board. Now if I raise the baud rate in picocom to 19200, we should immediately see that change on the cycle latch here and the cycle count. And when we cross that threshold of 32 edges, which is on this line, there we go. Ah, perfect. Ta-da! Okay, if we raise it again, yep, brilliant. Well, that wasn't such a bad fix, was it? I just got to make sure it's actually robust. Turn the rate down again. Looks good. Turn the rate down even further. Yeah. Cool. We do get some garbage at the changes, but I think that's kind of something you can't really avoid. Now then, if we are set to 9600 and we get a lot of data in all of a sudden, so we're going to set this, at a higher baud rate. So set this for a higher baud rate, 19200. And oops. Oh, I've just broken that because I pressed return inside picocom. Apologies. There we go. Okay. Right. Oh, interesting. There's a bit of jitter in there. If I keep pressing A, we do get a little bit of wiggle waggle. Anyway, never mind. Let's come back to that. So now we reconfigure the port for 19200, quit picocom, and put our hello into the port. What does that do? That recognizes it. No problem. There you go. Okay. I think that's a good fix. Let's have that fix. Get out of that. What have we done? We've put some registers in. We can ignore all of that. All we really want is this section here. So I'm just going to snip that out into a commit. Okay, right, next thing I think to do is just to confirm that frames with parity still behave correctly, because we've got the old behavior in there still. There are going to be situations where the parity is going to be high and the stop bit's going to be high, which means that you can't see it. So it's going to kind of potentially halve our recognition rate. Right, so let's just do that quickly. Glasgow run, auto baud, parity. Let's go for odd parity. Can't do that. Parity, oh dear. Yeah, there are a few garbage characters, so let's just do that again, just to talk about that one quickly. So if we go for 9600, we send a few A's, A. There we go, so we've now switched to 9600. We then increase the baud rate to 19200, we send a few A's. Okay, so we didn't see anything, but I think probably find there are some frames coming through that are just non-print. If I reduce the baud rate, there we go, we get a left chevron, left arrow, which should be A. So that's up here. So there is a bit of garbage, but that can't really be helped, I don't think. As I was saying earlier about the framing, if you receive a message like this, then there's no way you can tell that you're out of sync in terms of bit rate because stop bit looks like idle, basically. So let's put the parity in. Let's just try that quickly. Let's put, oh no, we had a problem with it, didn't we? What was the problem? Parity even. Error. Value bit sign not defined. I think maybe when I change this from nmygen, oh sorry, when I updated it to nmygen, I think maybe I never tried it with parity, so that's bad atty. Let's have a look. nmygen version, I can't remember what it's called now. Let me see if I can find it. I'm looking for the compat summary, that's the one. Right, okay, sorry, distracted by OBS over there for some reason. So it's complaining about value bit sign. Let's have a quick look in here, see if it's, yeah, there we go, value.shape. And that gives us, I presume, an unsigned or assigned based on what it is. And that's in UART.py line 140. Let's turn the scope off so you can see. Is that there? Sorry, distracted by OBS. Come on. No. Managed to drag a thing out the way. Okay, so in the gateware 140, here we go. So value bit sign becomes value.shape. I wonder if that's just going to work. Nope. Can't unpack non-iterable none-type. Oh. Now we go digging, unless anyone in chat can tell me what to use. Regarding changing or not changing when the difference isn't very much, I think that might be a good thing. Let's have a look at that maybe in a minute. I think that I just want to prove out, I suppose this is going to be yak shaving now, isn't it? Trying to get the parity working, which I failed to do, or failed to do previously and didn't even test it. So the options are fix up parity and then try it, or fix up the baud rate detection so that it doesn't actually update on a small change. Let's go with the latter. I think that's probably more on task, isn't it? So in that case, we want to put a sort of a window. We've got our value, we want to have a window on it. Say if it's more than, I would go for something like 5%. If it's outside of a plus minus 5% window, then we want to update it, but otherwise keep it. How would we do that in here? I don't think percent's the right way to go, but we could use an absolute value. So if we go for something fast-ish, we could also have a look at what values we're actually getting out as well. So let's do that quickly. I think this is going to be more of a problem at the lower baud rates. So if I just spam A's, there we go. So we do get 9615, 9626, 9634, 3617. The trouble is, if we raise the baud rate all the way to sort of a meg baud, for example, or 1.5, let's try that quickly. I think we will have only 32 clocks, 1.5 meg baud. think the scope's probably going to be, yeah, 600 nanoseconds it's picking up. So 1 over 600 nanoseconds is, yeah, 1.6, but it's not. It's not 1.5, but it's okay, whatever. So the issue here is that an absolute value will prevent us from determining or correctly shifting at the higher baud rate range, whereas a percentage change will work better, I think. Am I reasoning about that correctly? What we had previously was, let's just put them into Excel quickly, because I can't do numbers in my head, unfortunately. So we've got 9615, 9626, 9634, 9636. What else? This is baud rates, of course, not counters, which we should probably be looking at more accurately. Yeah, let's look at the cycle counter. How we can do that? 995, 985, 982. The 9600 sees between 982, 995, 5000, 4982 and 5000. So that there is a range of 18. And if we go for 18 ticks at 48 megahertz, is that, which is 2.6 megahertz. Yeah, okay, so maybe we could use an absolute value of about 20. The issue there, though, is that, as I said earlier, if we go for the higher baud rates, let's go for up for 3 meg baud, for example. Wiggling back and forward quite a lot there, isn't it? It is saying 3 meg baud, but it's also saying 2.8, and lots of frame errors. Let's just have a look at the scope, see what that actually says there. Starting to go wiggly. I said there were slow signals earlier, but 3 meg baud's not so slow. So that's saying 322 nanoseconds, so 322 millimilli. So, oops, sorry, 322 is just over 3 meg baud. So it is actually kind of in line. It's not bang on. Not something you probably want to use. What is that? 3 meg baud divided by that is, oh, it's still within 5%, that's okay. But the issue here is that it's 15, and we wanted to be using a threshold of 18 potentially. Is that realistic? What does a 2 meg baud value look like? That's 20. If it's more than 20 Hz, if I reduce that to 1.5, 31, yeah. Maybe let's not report it if it's within a percentage, because we can do that in Python much more easily than we can do it in MyGen, I think. My guess, why aren't programs fan of using 1,000 decimal points indicator? I always have a problem, see if it's a million or 10 million. Yeah, so are you talking about Excel or are you talking about my use of exponents? Are you talking about picocom actually? It probably makes a lot more sense, doesn't it? Yes, fully agreed. That is 2 meg. That is 3 meg. It does make it a little bit awkward, doesn't it? Yeah. You just have to read it very, very carefully. Select each character one at a time. So there's 3, 4, 5, 6, and then a 3 on the front. Okay, I think the decision then I'm going to take is that we only report it if the change is within or outside, sorry, a 5% window. Because otherwise we're just going to be reporting it loads. It's probably good that the gateware itself is actually following more precisely, because there could be variations or whatever on the bus. So I suppose you could end up in a situation where the baud rate changes very, very, very slowly across quite a large range, and you don't get a report. So what we need to do, I think, is store the last value that we reported and compare it with the new value. And if it's outside the range, then we report it. So that leaves us here. New bit psych, let's do, and new bit time is self sys.freak divided by new bit psych plus 1. So that should give us the new bit time. That's not the bit time though, is it? Sorry, that is actually the baud rate. So let's do new bit freak. And then we can also save a last bit freak. Last bit freak equals 0. If the new bit frequency is outside a 5% window, last bit freak is less than new bit freak times 1.05, so that's plus 5%. Oh no, sorry. I want to times this by 1.05. So the last bit frequency is plus 5%. What am I trying to do? If that's less than that, yes, that's correct. And last bit freak times 0.95 is greater than new bit freak. Then we report and we update it. Let's see how that looks. Get rid of this bit. Current bit cycle. Okay, so they were using that previously. Let's do the same thing then. But what we actually want to do is put this as the same equation. And we could potentially move that into a function, I think, as well at some point, just to make that a little bit cleaner. Let's pop this down where the old one was. Okay, run that. See how it goes. Oh, error. Bad. Boom. Local variable. New bit psych. Reference before assignment. New bit psych. Cur bit psych. Let's put that as cur instead of last as well. And then that becomes, just to keep with the naming. There we go. Nope. Oh, cut, whoops. Where did I put cut? Yeah. Ah, okay. Right, so we start off at 115,200 is the default. And if I go there we go. Have we seen a report though? No, we haven't. Oh, that's probably supposed to be an or, isn't it? Where I put that and. Here, so. And we probably, just for the sake of our brains, let's put this at the front, so it's the low end first. Or. I'm going to change these around as well. So we've got current value minus 5% is less than the new, or the current value plus 5% is greater than the new. Yeah, I think that works. Okay, switch to, there we go. Oh, it's saying it every time now. Why do these things always trip me up? I hate working with numbers, I really do. Okay. So low is current bit frequency times 0.95. Okay, so that's plus or minus 5%. I want to say if the new value is out of the range, outside the range, then update it. Yeah, it is like this. New bit freak is less than that, or new bit freak is greater than. Sorry everybody, I'll get there eventually. No, current bit, oh cut again, I've put misspell in there. Cut bit. There we go. Okay. So if I do A, there we go. So it's reported. 9632 baud. You can do loads of A's and it doesn't report. If we go up a baud rate, there we go, it's reported. Up again, up again, up again, and again. So it's more precise. It doesn't sort of snap to the value which, you know, the common values, which I think is kind of alright. It's giving you more details than you might want. 1 meg, go for it, yeah. 1.2, 1.152, 1.152 meg comes out as 1.2 meg, but that's kind of alright, I guess. 14545. Just out of interest, what does the scope say on 14545? It says 654 nanoseconds. Millimicro nano. Multiply by that, so 1.529. But again, we're limited by the abilities of the, or you know, the range of the 48 megahertz clock. 48 megahertz divided by 1.529 is going to be, oops, 0.529E6 is going to be a decimal. Hey Esden, things are going okay, thanks. Just trying to get my head around some numbers. Times 32. Yeah, okay. So I think, Esden, we have managed to resolve the issue you saw yesterday with the auto baud detection. The major problem was that you were sending individual more calculators, definitely, yeah. Yeah, so the issue you were having yesterday was that you were sending individual characters, and the problem with individual characters that have no parity is that the stop bit looks identical to a idle at a higher frequency or higher bit rate. So with an individual character, you actually sort of probably get some garbage, and then your line returns to idle, and then as the FPGA comes along and says, okay, there should be a stop bit here, it sees the idle line, it goes, yeah, okay, good frame. If instead you produce a burst of characters, so we did that with a hello just now, then you'd end up with transitions immediately, and the chances are that when you get to what you expect to be a stop bit, it's actually not. So what we've done so far is we have adjusted the applet so that it will update the baud rate, here we go. So if there's no parity, which can help with this, well, okay, so parity bits will give you a 50-50 chance, depending on the character you're sending or the byte you're sending, of picking up the problem. Because if the parity result is a 1, then that looks the same as an idle again. So if we've set the parity to none, then we just say if there's a new counter value, just use it straight away. If the parity is not none, then if we have a parity error and there's a new counter value, then update it immediately. I'm kind of wondering, to be honest, if we actually want to do this at all, if we should just always update it to the latest value. You might get potentially some problems with noise and stuff, I guess, but if you get noise, then your data is going to be wrong and your parity is going to be wrong as well, so that's not really going to help you. The other thing we've done is that Electronic Eel pointed out there was a lot of reports of baud rate changes, even though there wasn't a significant change. I'm not sure if I can find one in the history now. But yeah, running at 9200, for example, or 9600, if you send characters over and over again, then it keeps tweaking its bit time value. So what we've done is we just now put a there we go. So there's a ±5% threshold before it reports the new value based on the previous report. And I think that seems to work well. So let's just commit that as well, I think. We were going to move this though. Get bit frequency. Move this into a function because we don't actually want to look at the counter cycle, the cycles anymore. We want to look at the frequency and do a plus-minus percentage on that. Does it make a difference if we do it on one versus the other? I'm just going to go the other way, aren't they? I think it's in terms of sending characters manually, I think it's actually a use case that we can't say, oh, that's expected. Oh, that's no problem. That would have shown it work, yeah, but yeah. So I think we have to be able to deal with single characters. I'm not super comfortable saying that it has to be a bunch of characters at once. So yeah, let's just stick with this change we've made. Oops. Right, so if we look at the cycle value versus the frequency is only important for reporting. I think we can just use a cycle counter with its ±5% on it, can't we? Let's put that in there then. Don't even need that at all. Change freak cycles. I'm going to undo some of what I just did. The frequency becomes the cycles again. Pop that here. I think it was at the top, wasn't it? We can have a look at the diff in a sec. Don't need that anymore. A new bit psych. So change freak for psych. Oops. Yeah, that's okay. Yeah. There you go. Is that going to work? There we go, 9600. Turn the baud rate up. So yeah, Esden, you might have noticed yesterday that it worked coming down the baud rates, but not going back up. And that's this framing issue I was talking about. So if I turn the baud rate up now, it should, there you go, picks up the values. And if we go back down the range, you see a bit of garbage, and then there we go. Garbage, and then that. Yeah, cool. Now, if we stay at 9600 and just send loads of characters, because of that thresholding we're doing ±5%, we don't get loads and loads reporting. So let's Let's get rid of all this rubbish that I've added here. Let's get rid of these thresholds and just check that it still does a good job. I think it does. There we go. So A. Yeah. So this is the example here, where you get a new baud rate, which is really overly precise. Every 32 edges. Actually, it's probably less than every 32 edges because I'm just spamming it at the moment. Python is doing its loop sort of once a second, I think it is. And that's what we're trying to get rid of. So let's just put that back in. I think that worked nicely. Cool. That's another commit. Don't want that or that. Don't want that or that. Cool. Okay. Want some of this. Don't want any of these or those. Don't want that. Yep, we can do with the old code logo. And that'll do it. But you're lucky it works at all, because last time I tried, well, actually, when I was doing the nmygen port a while ago, I tried the auto baud and it didn't work at all. That's quite an interesting commit message if you want to have a look at it. UART down here, there we go. So the issue was, I can't quite remember. The counter was getting set to 0, and when it's 0, you can never beat a 0 kind of thing, and it was getting completely locked up. If you had the time, I suspect it would have taken a single bit time to be something like 894 seconds, I think it was. Oh no, a full word, so 10 bits would have been 894 seconds. So if you sat there and waited, I think you probably could have seen a full frame, but that's a really slow frame. So yeah, it works. It worked-ish on your stream yesterday. Right, okay, so I think that's cool. What we want to do then is only report baud updates when outside a ±5% window. How slow can we go? Right, now this was cool. I did have a quick play with that actually while you were going yesterday. Let's try and get rid of some of this garbage that I've put in. Just quickly clean it up a bit. Yep. Cool. Okay. Nice. Right. Now, due to various things, the auto baud detection and no bitrate specified. So there's 9600. I've actually just removed what I wanted to use. If I turn it down, we top out here at 518 or 5,859 baud, 5.8k-ish, even though we're expecting 4.8. That's really annoying that I've just thrown all that stuff away. I reckon I can grab it from my scroll back. Can have all this discard hunk question mark. It's not going to be a single thing, is it? It's going to be 1, 2, 3, 4. Yes. Let's try and apply that patch. Oh, it worked! Wicked. Okay. So if I turn these back on again, these will print out the values of the registers in the gateway, basically. So if we run it with auto baud, run it for 4.8k. Building. I'll turn the scope back on. Okay. So if I send some A's at 4.8k, I need to go and zoom out. Oh, that was unexpected. It reported 4.8k. There you go. So that's really slow. What have we got there? 207.7 milli micro. Yeah, 4.8K. So the FTDI chip is doing the patch works. Yeah, I wasn't sure that was going to work, but it worked, which is nice. So yeah, the FTDI chip is running at 4.8K. Glasgow now is getting just frame parity errors. Yuck, yuck, yuck. This cycle counter here is the problem. Okay, so if we have a look at that, it's topping out at 9,000 and getting quite unhappy. 48E6, which is 48 megahertz, is a 20.8 nanosecond period times 9099. I'm just doing this all upside down there. 4.8K. So the auto board is just about counting correctly. But if you look here, oh no, well, where was the problem? I think the problem is actually in the UART itself. So if we then dig into this one here. UART, here we go. The issue is that inside the UART we have a, let me get rid of the scope again, sorry. Inside the UART we've got the transmit receive sections or subunits, whatever you want to call them. And here we go, the RX timer has a range of max bit cycles. So it can count up to a maximum of, let's figure out what that value is. Oops. What am I doing? Max bit psych is going to be here, max bit psych. We've even got a nice comment. We support any baud rates, even absurd ones like 60 baud, if you want, but the applet will have to be rebuilt for anything slower than 9600. This is why baud rate is built as a build argument, even though the applet will never be rebuilt as long as you stay above 9600. So yeah, this value here I think comes out at 9999. Max bit psych equals. There you go. Oh, 4,999. Even worse. So we can't reach all the way. Now, I'm not super sure why this is here and why it's got a minimum of 9600. If we have a look at the bits involved in 49099, that's still that's a 16-bit value, or it could be as big as a 16-bit value, but it's definitely a, what's that going to be? 16, 15, 14, 13-bit. $1,200 baud is fairly often, is it? Is that things like the teletype that I linked? I'm not sure if you saw yesterday. The Curious Mark has logged into Linux over his teletype. Yeah, so 300 baud, I think. We actually, one of my previous companies I worked for, they had a current loop system which was down at the 300 baud type range. So if we were to give an argument of less than 9600 and the auto baud flag, I wonder if this would actually, let's put 300 baud in there, for example. I wonder if it would still follow correctly. So now we've got 160-ish thousand as the end point. The default baud is going to be 300 baud. There we go. So there's the A's. You can see the LED. Look at that. Oh, you know it's slow when the LED looks bright. Although you can't necessarily see it's bright because the desk lights are so. There you go. I'm just going to quickly do my little camera sync up. I found a way to do it without breaking everything. I just need to keep, there we go, so it's frozen. Now I get it going again. There we go. That's much better. Raspberry Pis, woo! Anyway. Right, where were we? Sorry, I got distracted trying to show you the LED going really bright because it's so slow. Right, so if we've set the -B, so the baud rate, to 300, and we've set auto baud as well, if I change the baud rate up, I wonder if it's going to follow. It does, yeah. So it still follows, which means that if you want a slow baud rate, just give it on the command line, and you can still use auto baud, that's no problem, which I think is fine. I was just a bit surprised, I suppose, looking at the code. I was just a bit surprised, sorry, looking at the code, that it produced this value, which was 4,999, which is a, what did I say, 13-bit value, but it wasn't running all the way up to, that's 4, 8. Yeah. Oh, okay, so that does only go up to 8,191. It doesn't go all the way to the 9,000-ish I think we needed. Yeah, cool. I'm happy with that. So I think that's probably the UART fixed. Oh no, the last thing then was the parity stuff. Do we want to still require an RX parity error and a change before we acknowledge the change, or do we just go for it? How low can the FTDI go? I don't know. Oops. It can definitely go to 300 baud. Let's put the scope back on. Oh, sorry, you're not seeing the right thing. There you go. There's the scope. There goes. That's 300 baud, and that's way off the screen. I love it. Grab calculator. 1/3.336 millisecond. Oh, 1/3.336 milli. 3.336 e minus 3. There we go. Yeah, it's 300 baud. Baud. Not familiar with that one. Oh, 150 baud, it seems to revert to $820 baud. Interesting. I think it does do 200 baud, which is there. 5-ish milliseconds. Yeah, 200 baud. So the FTDI happily go down to 200 baud, which is kind of surprising in a way. The other one, I think, if I go down, is it at the bottom? No. Doesn't do 110 baud. It's being naughty at this point. It's picking its own. I think it must be at the top end then. You start to get past the 1.5 baud, or 1.5 meg, sorry, 2 meg, 2.5, 3, and then you get to 3.5 in brackets 9600 baud, which is a little bit interesting, and that's 104 microseconds. So that, I can't remember values now, but that kind of feels like 104.19. Yeah, that's 9600. An early piano. Oh, an early piano baudot. Do you reckon I'm pronouncing that right? Keyboard. The baudot code, Bodo, is an early character encoding telegraphy. Interesting. Okay. Anyway, I think we played with that. We wanted to get the parity working. I think we sort of stumbled across that. If we put parity even, for example, it goes no, it's unhappy. Yeah, I know that. I think FTDI and a couple of others, you can give them sort of the direct values, especially on Linux at least. Windows does other weird things which I'm not fully au fait with. But there's kind of there's the one way which is using the hash defines the enum, I think, and then there's the other way which is actually configuring the divider or the clock divider correctly. Ordo. Okay, cool. Thank you, Exabine. Right, value bit sign. Let's dig in, try and fix that. I think I've got an margin checked out here. Oh, that's fine. Deprecated. Here, let's go while we're doing this. Use v.shape. Oh, v as in the value. What do we have previously? Value. Oh, okay, so I can't just do value.shape. I need to do x.shape as in variable. No worries. Thanks for coming along, Electronic Eel. Hope it was kind of interesting. Thanks for your input as well. On line 140 in Gateware, 140 is up here. So we want to do sig.shape, I think. That's probably what I did wrong earlier. Let's try running that. There we go. Great. I need to remember how to turn on parity, minus parity, odd, even, and none. So this is another interesting thing, is a lot of ye olde hardware can do, so the standards are none, no parity, odd parity, and even parity, and the odd and even are calculated based on the value of the data you're transferring in that frame. But then you also sometimes have old technology which does, or obscure technology which does a always one parity and an always zero parity. So the always one parity you can kind of emulate as a second stop bit potentially, or a bit of dead time between characters, which is sometimes difficult to control when you're dealing with things like FTDIs and PCs. But when you've got control over it, like an STM32 or some other micro, then you've kind of got reasonable control over it. But for the zero parity is actually problematic at that point. And there's even a 1.5 bit stop, I think, as well, which I don't think I've ever seen used, but it can help with certain things. I think there was an XB module at one point which couldn't keep up with a full-on stream of data, and their solution was to say, use at least 2 stop bits, which was kind of amusing. Parity. Right, so we're going to set, I can't remember what I did now, even. There we go. And if I raise the bit rate, it does see it. And it also sees the parity errors there. Oh, yeah, that's exactly the issue I was thinking we might run into, where we're getting the new value, but we're not actually latching it in because we're not seeing a parity error. So A in this situation is, oh, it's happened now, of course, but let's try and make that happen again. There you go, so drop down a bit rate and go back up. And we're, oh, anyway, never mind. So the issue is still present. And I think that because of that, let's let's ignore the RX framing and parity errors and just always follow the most recently measured bit time. There's even parity. Exabine, you said 8N1, so presumably that's, N81. So normally 8N1 is 8 data bits, no parity, 1 stop bit. Are you referring to something different, or did you just get the letters backwards? That's okay. working now. There we go. Yeah, brilliant. I think that's the solution then. Just don't look at the parity or framing errors because they aren't super helpful, I don't think, in this situation. Peace and love ink. Have a look at that. Not sure if there's supposed to be a dot on the end. Oh, ooh, okay. Yeah. No. Am I going crazy? Yeah, there we go. I guess they're both okay. Yeah, so 8 data bits, no parity, and 1 stop bit. And then you get things like 8E1 and 8E2, 8O2, etc. I didn't know that. Actually, maybe I did. It's ringing a bell. And you can load it into a computer, like a tape type. Yeah, that's cool. Right. Right, okay. What we're doing is that. No, yes. Vaguely, in terms of the touch tone jukeboxes, I'm vaguely aware of what you mean. Oh, okay. Oh, speaking of modem handshakes, Windy Tan, I think. Windy Tan modem. They did. Let's just grab it. There we go. This fantastic graph here. And I just love that. That's so cool. It explains every single bit. So here's the DTMF where you're dialing the number, is who's talking, you know, backs and forwards. But there's another one which I saw kind of recently, which is a like a waterfall plot of the spectrum as it's happening. Let me see if I can find it quickly because it's so good. Sorry, I won't look too deeply. If I don't find it quickly, then I'll just give up on it. This one, I saw it just the other day. No, never mind. I'll give up on that one. I'll try and share it at some point on Twitter or something. But yeah, that just looked so good. Both of them, they're awesome. Anyway, back to this. Right, so we fixed up baud rate. Oh, sorry, parity. We fixed up the auto baud. I think that's probably good. Is there anything else to do? Get rid of all of that. Just actually, let's stash it. Otherwise, I'll immediately want it again. Actually, my patch from before was okay, wasn't it? So we can probably do without that. Oops. Just clean it up a bit before we stash it. Yeah. Okay. What have we done? We've done these 3. There's the parity, there's the baud rates. This one, that is the auto baud on single frames. Yeah, because that's fixing up that one. That's only reporting. Yeah, okay, cool. I'll just leave it as that, and I will work on the commit messages because they're a little bit wrong now. Okay, that's nice. I was wondering about looking into feasibility-wise getting a frame buffer on HUB75. I'm not sure if that would be interesting. I did also do the servo stuff. How far do we get with that? Oh, lots of whip stuff going on still. Control servo ppm, there you go. I think this is probably done pretty much. ppm output, single channel. Yeah. Okay, so I think the servo one's pretty much finished. I just need to tidy it up and make a PR for it. The auto board, I will tidy up and make a PR for that as well as the parity stuff. We could come back to HUB75. Not sure if people would be interested in that. I'm kind of tempted to not go on for too much longer this evening. I'm not sure if there's anything else that we need to have a look at. That's just a basic video generator. Oh, sorry, yeah, the pattern generator. We would need to do frame buffer stuff. So let's have a look at that then. That is ICE 40. This is probably not what I wanted. ICE technology, this one. Yeah, so what primitives do we have available, and what kind of RAM have we got? Have we got dual port RAM, makes it easier, or have we got to deal with timing and access and stuff? This is something that I've not really done much of before. So if we have a look at the data sheet, I think it should probably say in here somewhere what we've got in terms of block RAM. Here we go. Single port, pseudo dual port, or FIFO memories with programmable logic resources. Oh, can you, Esden? Oh, okay. I wouldn't know how to do that. What can we do to figure this one out? Is it going to be in here? Possibly not. There's, I can't remember who it was, Robert, is that right? Some pretty good, good words on that in terms of getting started. Not done it yet, okay. Okay. You saw it in the lambda sock. Lambda with no T. If you had a link to that lambda, oh sorry, I'm not very good at spotting problems. If you had a link to, or if you had happy to have a rummage, that might be really good to point me at something. That's where I am. I suppose it could be sock. Shall we just clone it and then we can have a little rummage around a bit more easily, can't we? Right. Oh, look at that. Oh, it's in the examples. So it is. Line 36. I could have sworn I looked in the examples. SRAM peripheral is in lambda-soc perif lambda-soc perif SRAM. There we go. Yeah, okay. I'd quite like to just access it directly to be simple, if that makes sense. The stuff I did with Tiny FPGA, I got the frame buffer going, so let's have a quick look at that. Hattie, GitHub, Hattie, there we go. Memory. Yeah, okay, good point. Thank you. And mygen-soc. Oh no, sorry. That probably just comes directly from mygen, doesn't it? So in here, we can grab to memory. Ugh. Memory test case, class memory, HDL mem. That's promising. A word addressable storage. So the width, depth, initial values. What do we get out of it? Read port, write port. That's very cool. So we get a read port. Looks like this. We got address data and presumably an enable pin. Okay. Should we try? I don't see why not. I'm gonna give this a go. Easy peasy. Okay, give me a second. I'm gonna put you on the top down and I'm gonna just disconnect all this stuff because I think we're done with it. Actually, I'm just gonna transport this as it is to the other desk. Get rid of it quickly. And then I'm gonna bring the HUB75 stuff. I'm just gonna get rid of this, one sec. Okay. So this is from the stream the other day. It's still wired up. I'm actually going to remove, I've got two panels here at the moment, so I'm just going to remove one of them. I have to do something about power in a sec as well. Okay. Plug in Glasgow. Oops. Throwing it around, okay. Scope probe. Okay. Can we see most of that? I think we can. Let me get some power going quickly. Probably get some longer wires someday if I'm going to do more of this. Bit of a stretch. Okay. Okay, let's just remind ourselves where we were, I guess. Let's put the power supply there. So we're going 5 volts, 4 amps, that's good. And then we're going to do HUB75. That looks good. Pixel width is going to be 64. Pattern rate 2. Go! Ta-da! You want to see the easy peasy? I can almost guarantee we're not going to get it working tonight. So this is the procedural generated pattern that we were playing with previously. I fixed it up so we had one row which was out of place. Not sure if you remember, it was just shifted down once. And what should have been happening at the bottom was happening at the top of the half panel. I've added a couple of parameters, so now we can do things like the pattern rate, and then the pixel width and height as well. So because these panels change in size so much, I figured it was probably quite useful if I set the pattern rate to 0, you'll see here that every single pixel is sort of, it advances every single pixel. And then if I set the pattern rate to 1, it advances every 2 pixels. So if you have a smaller display panel or whatever, then you can use a smaller value. Oh, I don't know about that. I feel like I'm opening myself up to fail now. There you go. So that's a pattern rate of 4, and I think that's probably 16 pixels squared per thingy. So if you have a small 32 pixel or 16 pixel panel, then obviously this is not going to be appropriate, because you're only going to see yellow and blue potentially if you've got a 32 by 16 pixel. So this is what we did last time. What we want to do now is to put an image on that display. Now, I think probably step 1 is to instantiate some memory and put something which should be an image into that memory. Excuse me. One first step could be to stream the Twitch stream on the panel. The very first step, yeah. Simple. Okay, so looking at the code, what have we got? We've got the memory, SRAM peripheral, blah, blah, blah. There we go. I think we've got an init initialization option somewhere, was it? A list of int values. Initial values that power on each storage element in this memory is initialized to the corresponding element of init, if any, or 0 to otherwise. Now, it's very easy to just put zeros in, but that will probably map to just a black display, and that's not going to be at all helpful to what we want to do. So I think we've got 2 options. We can either try and wire up everything so that we can put an image through Glasgow, the application on software level, into the gateway, into the block RAM as sort of step 1, or we can just use this init parameter. I think the init parameter probably makes quite a lot more sense. So let's go with that. I'm going to turn the panel off because it's quite bright. Voltage, I need to change the serial number now. Voltage AB 0. Boop, there we go. So here we go, let's do it. Video, HUB75. Okay, I'm gonna make a copy of that, I think. So we're gonna have HUB75 test pattern and a HUB75 image or frame buffer. Let's do that. FB output. Video HUB75 FB output. And this is going to start off basically as the same thing. HUB75, HUB75 FB frame buffer. Ding ding ding. So the test pattern is now off. It was about 1.1 amps. I think with the test pattern on. Yeah, so 5-6 watts, 1.1 amps, that kind of level. It's amazing actually, 120 milliamps for a display or panel which is just completely doing nothing. It's not small quiescent current. Okay, we need to put this into the all so that we can actually run it. This is going to be video HUB75 Framebuffer, HUB75 FB I think it was, HUB75 underscore FB, there we go. Okay, and this should now do exactly the same thing as the previous one, but we are ready to hack it, basically. Oh, then they're pretty high quiescent current as well, are they? Oh, actually, I meant to say as well, I can, with the arguments here, you can increase the exposure delay. So if I set that, I think, to 10,000-ish, it gets even brighter. There's 2.5 amps. So nice and toasty. Cook yourself on it. I turned that down to only 100. Anyway, plan. Okay. We have a state machine to shift out a single row. We're just about to instantiate some memory. We've got the frame buffer pins. Let's just do this. What are we doing? Memory. Okay, it takes width, depth. So the width, I'm going to make it 8-bit, I think. Should I go straight for 16? Because we're planning on RGB 565, aren't we? What do these actually come in? And how many of them can we get? Okay, so actually we can't get a full, read data port. Right, we can get 16-bit, okay. And that's 4K bytes, so that's 256 by 16, 4K bits, sorry. 256 times 16, yeah. And I don't know how many of them there are. Kind of expecting it to tell us somewhere here, but never mind. Is it going to be in introduction? Features, here we go. 4K RAM bits. Oh, what have we got on here? Any ideas? Oh, jeez. That's quite a lot. HX8R, is it? Or HX8K, let's go for. Tell you what, we can check quickly. Oh, this reminds me. I have got the PCBs for the Glasgow CAN add-on. They've arrived. They're looking quite good. I have to say the KiCad text and font, it looks way bigger than it should be, if that makes sense. It's really clean. So that's lovely. I've got the masks as well, the stencil as well for the solder paste. And I today ordered the components to go on them as well. So that's really cool. I did swap out the LEDs because of availability issues. But aside from that, there's one issue I've come across, which is that the DFN footprint or package that I've used for the CAN transceivers, the only option is the variant with the voltage level shifter built into it, and the one with the level shifter built into it needs a pin that I've left not connected tied to the reference voltage basically, and so there's going to be a teeny weeny bit of rework there, which is really frustrating, but yeah, that was just an oversight on my part. Whoops. Yeah, exactly. So aside from that, I think it should be good to go. I'm not sure if anyone saw that stream, but we ended up with one port designed for the Bosch Vector pinout on the DE9, and the other one's designed for the OBD2 cable, so that could potentially plug directly into your car. So yeah, we'll see how that comes along. I've got the components on order. They may well be here in time for next week, so next week could be an assembly video, I guess, but I'm not sure if people want to see assembly or if they would rather see me just dig into some gateware. But anyway, sorry, that was a little divergent. Let's come back to what have we got? We got Glasgow. Yeah, it's pretty cool. I'm a little bit excited, a little bit nervous, because Yes, exactly. I think I will prove it out on the desk. I've got a number of other CAN devices here, so I can connect it up to some things and just make sure it's behaving properly. We've also got the ability, oh no, we haven't, we didn't end up wiring the silent pin up, but we should be able to take care of that in Gateware, no problem, so that's cool. You had good surprises? I have to admit, every time I do something with a car, I'm just nervous that the airbags are going to go off or something silly like that, you know. Taking some of the dash trim off around the steering wheel, it's like, ah! Yeah, probably a little bit more robust than that. Anyway, so we've got an HX8K in here, and this reckons HX8K has got 128K bit of RAM. I don't have engine controllers as an ECU, no, but I do have a couple of other things. Yeah. Oh. Right. This is 128K bit. No, 128 times 1024 divided by 8 is 16K bytes. We are going to be doing RGB 565, so that's divided by 2, so that's 8K bytes. 8 pixels, 8K pixels. How many pixels do we need? We got 64 by 64 is 4K, so we could actually fit in double buffering, or I could get both panels going potentially for a 128 by 64 panel. That could be quite cool. Anyway, for today, we want 16-bit by 4K, I think is what we're targeting. Get rid of some of these calculators. Oh, it's crazy, yeah. All of this vehicle stuff makes me nervous, I have to admit. Oops, what are we doing? Right, get rid of Excel as well. Get rid of this. Cool, okay. So 16, and we want depth is going to be 64 by 64 pixels. No, no, Alan, thanks for joining. Hope it was interesting. This is the bit where I start to go out of my comfort zone a little bit, but okay. Right, and then we've got the init array. So init equals. I don't know what that is expecting. I think it was a list of int. So to make this interesting, we're going to do RGB 565, and that's going to make our 16-bit word red, 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 green, 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 blue, 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 like that. So if we want to put a red pixel in the first slot, then what we want to do is a F800, and then we want a green pixel, which is going to be just random numbers. No, I want to. Oh, come on. I want to do it carefully. So that's going to be 7, and that's going to be E00. Oh no, it's not. It's going to be 070, and then it's going to be 001F, like that. So that's going to be red, green, blue, and those should be the first pixels. If we have the wrong size, what happens? Uninitialized memories are currently not supported. Fair enough. Okay, so we have to initialize it with something. Now we're going to have to do 0. I think this is going to work. 64 times 64 minus 1. Is that how it goes? Let's just check that out quickly. 3. So if we do a 0, oh, we probably need a 0 comma, don't we? 5. There you go. And if we have 64 times, let's just do 6 times 6 minus 1. There you go. Yeah. And then if we put a star on the front, so 1, 2, 3, star that. 1, 2, 3, blah. Cool, okay. It's not actually 64 to minus 1, it's 64 by 64 minus 3. There we go, okay. So that should give us red pixel, green pixel, blue pixel, and then just black. And I think that'll be okay for the moment. What we saw in here was that we need to get ourselves a read port. So source lock at, what does that make? Source lock at, I don't know, I'm just going to leave it as 0 or undefined. So fb read equals fb dot, what was it? Read port, like that. And then the read port has an address, the data out, and an enable pin. And the domain. Sorry, I'm losing myself here a sec. Oh, keyword args, okay. So we could give it a domain. If it's not combinational and it's not transparent, then we have to enable. Oh, we also have to give it a name as well. Do we have to give it a name? Name. Okay, so it does have a default name, that's fine. Cool, okay. So we got self.address, self.data, and self.enable. n.d.com fb.enable. I'm going to pop that wherever we like. Let's just put it here for a sec. Just check that we're really understanding what's going on. The address is going to be, let's just make that the X value, I think. So, thank you. Very good, David. Yep. Or David. I didn't ask you last time. Sorry, I'm an English person, and English people are rubbish at respecting other languages. Is it David or David? I noticed your L Blaze or L. I'm ruining your name. I'm going to stop. I'm sorry. Second, David. Okay. Apologies. fbr.address is going to be it's just count. Oh, I don't know how to read phonetics, unfortunately, either. And then the data. We have the data. The data comes out, and we need to put that, I think, into the output RGB. Now, let us swap out that for output.rgb1 equals, and we can do cat fbr data, and then we can take bit 0 for the red, and then we've got bit, so 0, 1, 2, 3, 4, 5. I'm taking the MSB from each color, and then 5, 6, 7, 8, 9, 10, 11. I think that should do it. Oh yes, thank you. Very good point. And that needs to be then equals count. Okay, so that should let us scan across. The bottom half of the screen should still be the test pattern, and the top half of the screen should be a column of red, then a column of green, then a column of blue. I wonder what's going to happen. Error. Int object is not iterable. Okay. Oh, that's because I didn't put the comma in there. Need to actually make it a tuple. A 1 cannot be used in assignments. Where is this? This is on line 78, which is here. It can't be used on assignments? was unexpected. I wonder if we need to actually... Well, I suppose we could put domain equals comb in there. Boom. And then we don't need an enable. I think that's how I'm reading it, at least. Something's not super happy. Oh! Okay. So what we ended up with is one half of the screen just black. There's no red, green, blue on either side. And the other is doing the test pattern as before. At least something has changed, I suppose. What's the problem here then? Let's turn that off. I'm actually just going to put this to 0, so it's just always black on the bottom, I think. We can leave it going until we get it running. Put the exposure down to 100 again. So the issue here, unused elaboratable. Oh, I never put it into the submodules, did I? m.submodules.fb equals fb, like that. I suspect that's the problem. No, something else is unhappy now. Read port created but never used. Memory is an elaboratable that does not explicitly inherit from. Doing so would improve diagnostics. Okay. Let's come back to our reference here where they're using a memory, aren't they? Here we go, self.mem. How do they deal with it there? They give it a depth and a width. And they get a read port is submodules memrp, which is fine. Address equals this. Doesn't look like they ever set the enable, and they never use the data, maybe. Not quite sure there. There's probably a write port going on. Oh, here it is, just there. The address is, there's the read address. Data is that. Okay. Fundamentally though, I think we're using it. Oh, hang on, we didn't put the read port into the submodules either. Let's do that. Oh, we got a green line. Well, that's kind of exciting. One green line, no red and no blue. But we can come back to that, I think. Yeah, so it turns out you need to put the read port and the memory itself into the modules, submodules, which is fair enough. Yeah, done both, so the memory's up here. What have we got wrong here then? Are we addressing it the wrong way? Does it go column first instead of row first, for example? If I put times 64 in there and see what happens. No, it's just all black. Okay. That was a little bit unexpected, I have to admit. There's a green line again. Let's put an F or an 8 in here and an 8 in here. And then we should get 3 green lines instead of just 1. Nope, still 1 green line. I'm going to put an OX800 in there, and everything should be green. Oh, that's interesting as well, actually. We've got green coming out, not red, because it should be red, green, blue. No. So what have we actually got here? RGB is a set of pads, and it is red, green, blue. Let's put in here a OX01. We can just get away with a single nibble. I think that should be blue and just everything blue. It's red, okay. In that case, that's wrong. Well, my brain is wrong at least. So an OX01 equals red. What does 2 equal? Probably green. Yep, okay, green. OX02 is green. And OX04 equals blue, question mark. Let's just confirm that. Oops. I think memory should not be a submodule. I don't think it resolved the issue. Okay, let's have a quick look at this again. Oh yes, you might well be right. Yep, fair. Let's take that out of there. There you go, so we got rid of that nasty warning, which we couldn't quite understand, or at least I couldn't quite understand. Okay, here is our output, and if we do a cat 11 or 100, that's probably going to be red. That's red. I think this might be a bit ordering thing again. Getting my head all broken by it. Red, and that's green. That's going to be blue most likely. Correct. Okay, now that we know this, we can pop in the fbr.data 0, and that should enable the red that should enable red on just everything because of the data we put in the initialization there. Think nothing. So we had, let's just draw on this, I think. Oops. So this is 0. This is 5. Oops, 5. No, it's not, it's 4. This is 8. And this is 12. Now, 13, 14, 15, yeah, so 15 is either going to be the most significant bit or the least significant bit. I always have to figure this out, it's kind of annoying. I need to write it down somewhere, put it on a big poster. Okay, that's red everywhere. Red everywhere. So the index is here, to the what's effectively an array or a list, zero is the least significant bit and higher numbers are more significant than zero. Okay, so if I do fbr.data and we put in there the green, so 8, 9, 10, we should hopefully get a single column of yellow because red plus green. Oh, okay. It's one column out of alignment, which is unexpected. This is probably a off by one type. Yeah, I think it might well be. Okay. And then the last one is going to be not 0, it's going to be 4, and that'll be the blue. So we'll have yellow, purple, and the rest red, is my prediction. No, just yellow, red. Okay, so if I turn this off like that, you should get just the yellow pixel and nothing else. Oh, the blue is really dim on here? No, that was something else I was working with. There we go. If I turn that off as well, we should just have green. Boom. And now if we do count -1, we should get red green, I think. Maybe. Oh, red purple. That's annoying. Not sure how well that's coming through on camera. I can do a little bit of this maybe. There you go. Yes, that's kind of a red purple, which is a little bit unfortunate. Red purple, so that's blue and red on at once. Cyan, purple, whatever you want to call it. That is this one. So that is correct. So if I turn that off, what do we get? Ah, I know the problem. Yes, okay. Count here is actually counting twice. Why is it counting twice? I don't remember. We're counting twice because we're using the very lowest bit there for the clock. I've wound the aperture down. I'm not sure if that's more visible. I could have a piece of paper. I don't have a piece of paper, but I do have one of these fuzzy panels I used for them in the past. A bit large though. Oops. How's that? Oh, that's maybe better. Wind it down again a bit further. There you go. Okay, so yes, as we were saying, the counter, we use the least significant bit of the counter as the clock. Not ideal, could be changed, but let's go for 1 to the end. And then hopefully we will get red, green, blue. Oh, sorry, you weren't watching the code, but I think it's being covered in words. Oh, red, green, blue, look at that. How exciting. Okay, what I had to do is just put this in here. So because the count, the least significant bit of the counter is used as the output clock, just going from the first bit instead of the 0th bit. That's really exciting. I'm pretty happy with that. What we could do then is potentially we need 2 read ports. Can we do 2 read ports? Can we do R1 and R2? Because we need to do 2 halves of the display at once. Oops. R1, 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 and then R2. So R2 is going to be, what's it going to be? It's going to be Aha, thank you. That's probably a good thing to look at, actually. This is what the example. PDM to fade LEDs. There's going to be a memory in here somewhere. There we go. Oh, gamma table. Oh, okay. Yes, cool. Okay, so we got 2 read ports, and that should be fine. Now the second read is actually going to be shifted by 32 rows. So I think just a plus 32 in there, is that going to work? Yeah. But what we actually now want to do is, this is going to be the top half. Let's just do that quickly, just make it run. It's going to be black though, because we haven't initialized that portion of the memory. There we go. So we have the first row, or the first half, sorry, I should say. And let's go for 64 by 32. And let's do this backwards. So it's going to be 001F, it's going to be 07E, and then it's going to be F800. And that's then going to be that as well. And I think now we should have red, green, blue up here, and then we should have blue, green, red down there. No, my math is probably wrong. What a surprise. It's not plus 32, is it? No, it's not. It's 64 times 32. We need to offset that by. Because plus 32 is just one row. Still not working. Let's make all of these pixels, well, let's just make them white. So we've got red, green, blue, white. So this should just be all filled in. Plop, like that. That looks all right. Red, green, blue, white. And then the second half, we need to fill that in somehow. If I put the white in there as well, what's going to happen? No, okay. We're clearly doing this wrong, or I'm clearly doing this wrong. Count is the column. Nothing to do with rows here. Just using the column. So if I was to do... Oh, sorry, I'm being a complete muppet. We haven't actually put any data on the second RGB board. So R2 data 15, R2 data 10, R2 data 4. What do you reckon? Yeah, look at that. Simple. Turn those white patches off as well. Oops. Okay, we have 3-bit color depth working. I wonder if there's a good image we can put on that display now. Previously, what have I used? I used LED matrix, just grabbing from a previous project. Apologies, one sec. Resources, here we go. So I drew out Ger in the dog suit is obviously my avatar. So there's Ger in a dog suit. I also drew out some pretty simple things like just a simple bar. A border line, that's pretty handy actually. So you got a single line on each border, and that works with our 3-bit color as well. So let's have a go with that. I'm just gonna grab that Where am I going to put that? I'm going to put it here. Edit in Paint, because Paint is actually surprisingly pretty good for this kind of thing. It doesn't do nasty aliasing and bleh. It just does pixels, which is brilliant. Okay. Like that. What do you reckon? So that's a 64 by 64 image with a red top, yellow, blue, green. We can save that, and now we're going to need to convert that into a string of, or not string, a list of numbers, integers. So step one is to grab it. Copy, sorry, I need to copy it between systems quickly. Glasgow. Borderline, there we go. And this is the kind of thing that pillow works well for. Not that kind of pillow. I'm just going to have a drink of water. So the idea here is we're going to open the PNG in Pillow and then grab each pixel out of it and convert it to the HUB75 value that we want, and then produce the tuple, which we're going to then dump into the Glasgow applet. I think I've probably got HUB75 RGB565 fb.py. I think I've probably got pill installed already. No. Okay, in that case, bin activate. What is it? Pillow? Or pill? I never remember. Installation. Pillow. Okay. There we go. Cool. What's it called? We do the border underscore line. And this is lazy, I completely admit, but we're just going to hard code a bunch of things for now. The image.open, whoopsie, image.open, and now we need access to the pixels. This will return returns an image object, out of which we can presumably get the pixels. I can never remember how, because I don't do it often enough. Get data. Yeah, go for that. Containing pixel values. The sequence is flattened, so the values are for one line followed directly after values for line. Can we get an XY type? Oh, we can do get pixel XY. Let's just do, I can't remember what it's called now, get data. That was called HUB75, there we go. Okay, that looks like our pixel data, and it's in RGB24 or 8888 or whatever you want to call it. That's alpha, red, green, blue, I think, probably. If we have a look at our image again, the bottom line is blue. So I would expect. Oh, okay, so it's actually probably RGB alpha, because they're all 255s. Okay. RGBA, like that. Don't care about alpha. Oops. Yeah, so bottom line is blue. Then we have just above it a single green pixel, followed by a yellow pixel, followed by loads of black. Perfect. Now what we want to do is do the conversion. Ooh, that's a very good point, thank you. Pi on 3. Oh. So what? Colon W, exclamation, Python 3. No module name pill. Oh dear. I think it's possibly not picking up the virtual environment. I might have started Vim too early. Yeah, there you go. Okay, neat. Thank you very much. I learn something every day. Okay. First step first, we need to shift the red down, so it's going to be 5 bits instead of 8. So it needs to come down 3. Let's just do it like this. Then the green comes down 2, and the blue comes down 3. Now we need to merge them, so we put is going to be. We do a concatenation or something? No, don't worry too much. Got them written out here, so it's going to be 8, 9, 10, 11 bits. Board with green, which comes 5 bits. Board with blue, which comes 0 bits. And we do print. Let's just put that here. Oops. Look at that. Right, these are not the kind of values we want because we want them as hex. So we can do colon 08x, I think. No, 016x. No. Sorry, 04. I'm getting tired. It's probably bedtime soon. Nope. There we go. Yep, so blue, red, green, blue. Blue looks like that. Green looks like that. Yellow looks like that. That's looking nice. Okay. Now we can just do this, and we can do print RGB 04x. With a comma on the end. Actually, I'll tell you what, we can put this into a list of pixels. And then we can do a join at the end, so we can just then do print, what do we want to do? Init value equals thingy, and then we can call pxlist.join with a comma. Final, no, I don't need a final comma, like that. UF while passing on 23. Oh, no, close the brackets. No, join. Okay, comma, sorry. Dot join pixel list. It's funny, you go on a break for a little while and you forget how to do everything. Okay, there you go. Those are our 64 by 64 pixels. I think if we write that to a file and we put it into Glasgow, software Glasgow, applet, video, HUB75 Framebuffer, and we do init fb.py, I think that'd be nice. Now we can do from.init fb import, I can't remember what it's called, init value, and we can just pop that in here. What do you reckon? Is this going to work? I'm nervous. Thank you, David. Yep, that's a good point. Let's do that. Boop. Init FB. Yep, looks good. Nice. Yee! Who's watching? I'll put you on here and then you can actually see it. Ding, ding, ding. Oh no! Oh, I know what the problem is though. I haven't considered the row that we're currently on. This is okay. So when you're bringing up a frame buffer for the first time, I do a lot of stuff with LCDs and that kind of thing. When you're doing a frame buffer and you're bringing it up for the first time, this is exactly the kind of thing you want. You don't want to jump into a picture straight away because it would be so hard to understand what's going on here if you just had 2 lines of a picture. But because we have 2 lines of a known image, which is this border that we've drawn, we know immediately that what we have is the red is just smeared all the way down the top half, and then the green and the yellow is then smeared all the way down the second half. So the problem is that I'm not considering the current row, I'm only considering the current column. So in this address here, we want to add in the current row. And that is going to be somewhere. Row disp, I think it probably is. Oh no, it's going to be row. So in here we then have that plus row times 32. Row times 32. And this also then increments it. Oh no, it's not going to be, sorry, it's going to be 64 times row. And the second half of the display then has to make use of an extra 32 rows effectively. So, moment of truth. Boom, look at that. That is so good. We have a frame buffer. We have no way of getting data into it yet, dynamically, but we do at least have a frame buffer. Turn that down a bit, even more, than you can actually eventually see some color. Cool. Right, 3-bit frame buffer. What else can we put in there? Previously, I've played with all sorts of things, so I did a colorful alphabet. There we go, these ones are cool. Drew a little bee, got my cows, got Gur riding a pig. I drew out Mario and Princess Peach and stuff. My avatar, should we do Gur? It's not going to look very good because we've only got 3-bit depth, but it should come out, I think. Let's do it. So here's Gur in dog suit. Nice and huge copy of it. Let's put it here. Let's resize it to oh, I can do pixels. That's okay. 64 by 64 pixels. There you go. That looks rubbish because paint is like that, but that's fine. Don't care too much. Let's pop that into Glasgow, and then we're going to use Gur dog suit. Oh, it's exciting, this. we will need to update the script, that is, sorry, so that it's no longer looking at borderline, it's now looking at dog suit, because we didn't deal with arguments, but kind of lazy, don't care too much. Not enough values to unpack. Okay, so we've no longer got the alpha in this image. We've only got RGB. That looks like it happened. Again, immediately you run into problems. Like, now that we've got an image, we can't just look at this data and necessarily think, yeah, that is exactly what I was expecting. White is white, which means, sorry, you're not watching the right thing. White is white, which means that you've got FF, which is great, but then we immediately sort of crash into 528A. What does that mean? That's obviously black, etc., etc. So it becomes a little bit harder to verify the input as well as verify the output. Right, let's run this again with Gur in there. See what it looks like. I am quite aware that this display is also upside down. So, oh, look at that. That's not so bad, is it? How does it look compared to what it's supposed to look like? I think it's all right. Let's try and turn this the right way up. Still look okay, yeah, that's all right, isn't it? Look at that. So, that's cool. I'm quite happy with that. It's a little bit strange. Yeah, I mean, as I said, so we're looking at the most significant bit of each pixel, which will give us the best mapping between the RGB 565 to effectively RGB 111, which is what we're currently displaying. If we were to pick out an individual other pixel, yeah, we got a frame buffer working. If we pick out an individual other bit of the pixel, then we're immediately going to start seeing weird stuff. So, oops. Let's just do it, because then we can have a play with it. So if we pick out the LSB, for example, so the red is going to be bit 11. Green is then going to be bit 5, and blue is going to be bit 0. Then this is just going to look like garbage. It's not going to even be recognizable, I don't think. Run it again. There you go. Yeah. It is recognizable, but only because of the extreme colors going on. Anyway, cool. So I'll put that back to how it was before. There you go. Now, to get any kind of color depth in these displays, I talked about it before, but you need to wiggle your pins, and you need to just really go for it. So this is the write-up I did previously. So here's the RGB 565, the pixel format that we're using. Driving the LED matrix, I can't remember quite which one it was. There we go, this bit here. So you end up in this situation where you have to clock out the least significant bit of each of the red, green, blue, expose it for, say, 1 time period, 1 millisecond, and then you clock out the next most significant, or next least significant bit, and then expose that for 2 time periods or 2 milliseconds, and then clock out the next and expose that to 4. I'm not sure if we could deal with gamma by doing this, but I know that TNT has done quite a bit with these panels, so it might be that we can apply gamma in the FPGA using these timings. But I suspect what I did previously was I applied the gamma before I pre-processed the image, and then I squirted it into the FPGA over a UART. And that worked quite nicely, to be honest. So I think that's probably a good stopping point for today. We've got a frame buffer. it is only 3-bit color. Not sure if there's something else more suited. Maybe maybe a Nyan cat or something. We go for a Nyan cat, one of these guys, because they've got some good colors in them. Let's do that quickly, just a little bit of fun. Put it in the middle. Come on then. Oops. Nyan cat rainbow. Yeah, oops, got a dot in there. There we go. So run this again. Oh, look at that. That's much more recognizable. We're still missing some of the details, so there should be a purple stripe here, I think. And this should be much more pink than white, etc. But yeah, doing a good job. Cool. Okay, so I think that's probably end of today. Next week, I'm kind of hoping that we will have the components for the Glasgow can add-on. They should be here. I'm not sure if I'll build it off stream, or maybe I'll sit and just chat while populating the board and then cooking it. I'm not sure yet. I think I'd quite like to keep going with this Framebuffer thing if no one minds, if no one else sort of desperate to do it themselves. It'd be quite cool to get that working nicely. So I think that probably wraps up for today. But yeah, thank you everybody for coming along and joining the ride. We got the UART done, which is awesome. We got at least we've got an RGB565 Framebuffer, of which we're only using 3 bits. But yeah, good start, good start. So yeah, thank you very much, everybody. I will be around and see you next week. Bye bye.